In the previous lectures, we have learnt about magnetic field, and the equations satisfied by it. The equations that magnetic field B satisfies are divergence of B is 0 and curl of B is mu naught J r, where mu naught is the permeability of the space and J is the current density. This is known as Ampere's law. And its integral form is that B dot dl over a closed path is equal to mu naught I enclosed by that path. In this lecture, what I want to do is learn about transformation properties of magnetic field under rotation and reflection. By reflection, we also mean inversion. Why is this important? Because this distinguishes magnetic field from a regular vector. It tells you that it is a pseudo vector, and learning about these transformation properties is important, because if there is a symmetry in the problem, these transformation properties can be applied to learn about how the field is going to be, what components are going to survive, what components are not going to survive. So, that is why learning about these transformation properties is important. So, let me just first motivate what we are looking for. We are talking about transformation properties of B. So, let us first see what a vector does. A vector is like the displacement, velocity, acceleration, and so on. So, under rotation, and just to recap, I will just take rotation of around z axis. What you have learnt is, if I have a frame, let us say this is x axis, this is y axis, and the z axis is then coming out of the page, and if I rotate this frame by an angle theta, then for a vector, let us write that vector as v, that has v x component plus v y component plus v z component. These components transform, as vector remains what it is. So, let us say this is the vector v, which I am showing by blue, but the components transform. So, v x prime, which is the new component, is going to be given as v x cosine of theta plus v y sine of theta. V y prime is going to be minus v x sine theta plus v y cosine of theta, and v z prime is equal to v z. This is how these vectors transform under rotation. I am just for simplicity taking rotation about the z axis. What about reflection? So, let us ask about reflection. Again, I am going to take one particular reflection. So, again I am given this set of axes x, y and z coming out, and let us say I reflect about the y axis. In that case, V x prime is going to be equal to minus V x, V y prime remains V y, V z prime remains V z. So, the component perpendicular to the reflection plane gets changed as sign changes. You notice that in this case, I am not saying what am I reflecting. Am I reflecting the system or am I reflecting the axis? If I reflect the system, a point from here goes here. If I reflect the axis changes direction. So, before I go any further, let me just tell you about what two ways of transforming are. Two ways of transforming are: number one, active transformation, and two, passive transformation. In an active transformation, the system, that means if I have a ball, if I have a vector field, whatever, undergoes the transformation. When I talked about the reflection, for example, in that case, if I had a vector v, this will undergo transformation. That means this will be rotated by theta. In the passive transformation, recall just now from what we did, it was the axis which rotated. So, in a passive transformation, the coordinate system is transformed. The coordinate system is transformed. Similarly, for reflection, what did we have in reflection? I had this y axis, I had the x axis, and I was reflecting about the y axis. If I transform the system, what I would be doing is taking a point here to the point on the back side, and the axis will remain fixed. On the other hand, so this will be active transformation. On the other hand, if I did passive transformation, the axis would change. Right, so this will be passive transformation. I'll go x the other way. In both cases, you will see that the component picks up a negative sign for a vector. If I am doing an active transformation, a vector which I am showing here now by green color would transform like this. X remains the same, so its Vx component changes. On the other hand, in a passive transformation, the vector remains as is. I am again thickening it, but the axis changes, so again the component picks up a negative sign. So, these are two ways of looking at a transformation. So, what happens to a vector? Let us go back to transformations again. So, transformation of a vector. In this case, I have given you the rotational transformation. So, let us recap it. Rotation about the z axis. In the active case, since the system is rotated by theta, it is as if the coordinate system has gone back by minus theta. So, if I just make a picture and a vector, I have rotated the vector by an angle theta. It is as if the coordinate axis has been rotated by minus theta. So, in this case, V x prime will be equal to V x cosine theta minus V y sine theta, and V y prime will be V x sine theta plus V y cosine of theta. Passive I have already written. How about under reflection? Under reflection, suppose I have a vector pointing in x direction, I am reflecting about the y direction. This is x, this is y. After reflection, the vector becomes like this. This would be active transformation. On the other hand, if I had a vector parallel to y axis, it remains the same. If I had passive transformation, in that case, this will be new x axis, x prime. Again, you see that vector remains like this. So, vector has flipped sign with respect to the axis. It is now in negative x direction, and the parallel component still, the component parallel to the plane of reflection remains the same. This is transformation of a vector. What about vectors formed by taking cross products? So, let me just give you the answer first. These vectors transform like regular vectors under rotation, but differently under reflection. What are the examples of such vectors? Examples are angular momentum, which is m r cross v. You can say, for example, magnetic field, which is proportional to j cross r minus r prime, j being proportional to v, the velocity, it is like a regular vector, right. So, these are vectors which have different properties under reflection. You can see that very easily, and I'll just build that up now. So, let us examine these. These are known as pseudo-vectors. Let us see how these properties differ. So, let us take the angular momentum. L, which is m r cross v. Let us say if we transformed by reflecting about all three planes, that is x y, y z and z x, all three planes. So, what are we doing? I have these planes x, y and z, and I am reflecting about each plane. I am reflecting about x y plane, I am reflecting about y z plane, and I am reflecting about x z plane. This is like taking a vector r and changing all its coordinates, or in a passive way I am changing the direction of all x, y and z. So, after reflection, the cross product follows left hand rule for direction. That is, direction of x cross y is given by turning fingers of left hand from x to y and thumb gives the direction of x cross y. This is in contrast to right hand rule, where this is done by right hand fingers. So, I have collected everything. Now, let us see what happens in this case. We are talking about angular momentum, L equals m r cross v. So, under inversion, that is reflection about all three planes one after the other, r goes to minus r, v goes to minus v, and therefore, L goes to m minus r cross minus v is equal to m r cross v. So, L does not change direction under inversion, implies L is a pseudo vector. Why? Because still under rotation about an axis, it still transforms like a vector, but does not do so under reflection, because it is not changing sign. So, it is a pseudo vector. Let us understand why that happens. So, let us understand why a vector formed by a cross product, and now I will write what this is equivalent to. This is equivalent to the direction of the vector being determined by some sort of rotation. That is why you turn your fingers in that direction of rotation, right. So, y a vector formed by a cross product, which is equivalent to the direction of the vector being determined by some sort of rotation, does not change under reflection. I said under reflection, I am cheating. I will cut this and say under inversion. And now, we will examine what happens with individual reflections. So, let us examine what happens under individual. Reflections. So, let us see. Let us take the xy plane as we have been doing. Let us take the reflection about the y axis and examine different components of L. The angular momentum Lx is given by m y v z minus z v y. Angular momentum Ly is given by m z v x minus x v z, and Lz is given by m x v y minus y v x. Reflection about the y axis. What does this give me? This gives me x going to minus x, no matter which way you look at it, active or passive. And when I do it physically, I will explain this. Y going to y and z going to z. Same thing is true for the component of v vector also, and therefore, Lx will remain as Lx, Ly would become minus Ly, and Lz will become minus Lz. So, let us see what happens when we do this reflection about the y axis. I had this coordinate system y, x, and I am reflecting about the y axis. Then the Lx component remains as is after reflection. Ly component changes direction, and Lz component, let us say, was coming out, starts going in. This is a pseudo vector. I am doing angular momentum because it is very easy to understand. So, let us see what is happening. Again, let me make the y axis, the x axis, if I want the L going in the x direction, this, and I take a disk, this disk must be rotating like this, as shown. The dotted line or dashed line shows the back side, and therefore, L is in x direction. When the system is reflected, so for example, if I look at it by reflecting it in the mirror, so what is this? Active transformation. Then still the system would look rotating like this, and therefore, Lx would still be pointing in the same direction. If I were to look at Ly, then Ly would be given by a disk rotating like this. Again, the dashed line or dotted line gives me the back side. So, Ly is pointing up. Now, let us see when I reflect what is happening. When I reflect, the reflected rotation would look like this. So, disk is now rotating the other way, and Ly would point down. You can argue the same way for Lz. That is a pseudo vector. So, whenever there is a rotation involved, this will do so. Let us look at the same thing from a passive point of view. Passive transformation. Again, I have this axis x, y, and x prime would point the other way. So, x prime, now I am transforming the axis, and here is this disk rotating that had Lx going to the right. In the rotated frame now, in the reflected frame or reflected coordinate axis, now I will be using left hand rule. Let me write this with the green. Left hand rule for determining direction. If I do that, you find that Lx is pointing in the x prime direction. So, Lx points in the positive x direction when you look at it passively. How about looking at rotation? Now, system remains where it was. How about looking at rotation such that the angular momentum is in the Ly direction or y direction? Again, when I look at it from the reflected frame, now I will use the left hand to determine the direction of Ly, and that gives me Ly prime pointing down. So, you see it is in the negative y direction. Again the same thing, the two different ways of looking at it, active transformation and passive transformation. So, I have given you a physical feel of what happens when you apply these reflection transformation or inversion. Inversion would be a combination of three transformations, and I will leave it for you to work out how they transform. There will be one time it will be parallel, then perpendicular, then parallel across the reflecting plane. So, that I will leave for you to work out. But you see how the directions come out to be the same. So, in a pseudo vector, let us summarize this. For a pseudo vector, reflection about a plane leaves the sign or the direction of vector perpendicular to the reflecting plane unchanged, and the direction of vector parallel to the reflecting plane flips. That is, component picks up a negative sign, and this is very unlike, or I should say in contrast to, a vector where perpendicular component changes sign and parallel component remains unchanged. And inversion, that is r going to minus r, is equivalent to 3 reflections, and it is now left for you to check that how components of a pseudo vector change under inversion. Figure out using 3 reflections. I am leaving that as an exercise for you. So, let me just summarize this lecture by saying that we learned about transformation, properties of vectors. Actually, this was reviewed, and pseudo vectors. In particular, these become the rule of thumb. Pseudo vector components transform like vector components under rotation, and pseudo vector components transform differently. In fact, we should say exactly in contrast to vector components under reflection. And let me explain that a little further. In this case, parallel components to the reflecting plane change sign and perpendicular component to the reflecting plane remains unchanged. So, I have shown this to you mathematically, and I have tried to give you some sort of an intuitive feeling as to why this happens, and we will now apply these to magnetic field in the next lecture. Thank you.